Hello and welcome to this week's Focus on Geothermal Energy for the Weekend webinar. My name is Alexander Richter. I'm the founder and principal of Think Energy. I present here on behalf of Enerchange and Think Energy, a partnership on this webinar series. Today with us is Ismet Yucetas from Middle East Air Drilling Services out of Istanbul, Turkey. He's the founder and CEO of the company and will present today on injection of non-condensable gases in geothermal reservoirs. For the participants, you have the opportunity to ask questions in the questions option in the dashboard of the webinar. We will then try to group those questions in the best way forward to give Ismet the chance to answer some of those questions after the webinar. And with that, I'm handing over to Ismet. Thank you for being with us today, and the floor is yours.
Thank you, Alexander. This is Ismet from Middle East Air Drilling Service. I am a petroleum engineer, actually, background with underbalance drilling and some reservoir engineering background. Today, we are going to just talk on one of our case study, actually currently working still as a how to inject NCG non-compressible gases to back in the reservoir, geothermal reservoir, which is produced in reservoir power plant. I want to just briefly say our outline today, what we're going to discuss. Basically, what is the importance of NCG for geothermal reservoir management is, and why we have to re-inject NCG in geothermal reservoir. And when after we ask why, and then the next question is going to be how we're going to re-inject NCG into the geothermal reservoir, and our pilot study and result and conclusion. I think if you look at the countries who producing a direct high enthalpy reservoir, producing a high amount of direct electricity, most of them have a huge amount of NCG coming with the brine as well. So actually CO2 is directly related with the capacity or enthalpy of the reservoir itself. Of course, it's dependent on the reservoir's formation characteristic. As may some of you know, the CO2 reinjection has been used in oil and gas to enhance recovery, and CO2 and other NCG gases are very strong greenhouse gases, but for most of the current geothermal system, after condensator, they have been released to the atmosphere, unfortunately. I am going to talk with one of our case, which is in Turkey. I want to just a little bit give a big picture of Turkey power plant geothermal reservoir characteristic, NCG characteristic, let's say, and it's mostly CO2 from 97 to 99.9 CO2. Some of them has a partially from 1% to less than 0.01% H2S. Some of them have some minor other gases, inert gases, changing from different type of non-compressible gases, let's say. The main reservoir gases coming as NCG is CO2, and specifically in Turkey, let's say, or in Italy, since reservoir itself is a carbonate, and carbonate due to pressure, temperature, enthalpy, it could be carbonate, could be bicarbonate, which is actually releasing one carbon dioxide after reservoir temperature pressure change. It can easily release or capture another carbon dioxide, which is actually make the brine with concentration of or the percentage of the in weight in the brine as a carbon dioxide. CO2 is not known actually a good gas. Everybody have a not good feeling for it, but in geothermal, actually, if it be managed at surface, it is one of the best part of the geothermal system, which help to produce naturally without any pump. CO2 is a special molecule. It is after 33 degrees and after 76 bar pressure, it is become a natural pump since in reservoir condition, it is supercritical state. Supercritical state means actually its physical characteristic is like a fluid, but it is real chemical characteristic is a gas. It's highly mobile, highly affect the, let's say, porosity permeability, inside porosity permeability mobility, and it easily change the phase in the, let's say, when you produce in your way up to surface, which help to expand in volume and which help to produce, make a natural pump for operating a reserve power plant in geothermal. Now, why we have to re-inject? It's important for strong enthalpy power plants. Why we re-inject NCG in geothermal reservoir is that a geothermal reservoir actually happen in, let's say, million years. There is a balance of enthalpy, balance of pressure, temperature, formation, material solubility. A sustainable geothermal production with CO2 re-injection is something a must, a kind of. Geothermal reservoirs, you actually produce your brine. 99% of the water, or let's say almost 100% of water is re-injected, except testing losses. You usually, if you have a re-injection well, you pump all of your brine back. But if you do not have any setted surface infrastructure, you don't re-inject back your NCG, which is mostly carbon dioxide. Depend on the your reservoir characteristic, your brine CO2 or NCG percentage, usually, which is in our case was in Turkey, let's say it was around 1.5% CO2. And if you think that for a long term, let's say one geothermal reservoir full circle is changing from 60 days to, let's say, 6 months. So each 6 months, you're losing 1.5% of your mass balance, which is affect for the reservoir pressure condition, which is affect the enthalpy, which is affect the energy concentration of the reservoir. And after all this, it's very clear re-injecting NCG to the reservoir, the geothermal reservoir, is a key to make it a sustainable as a kind of real renewable and forever, if you have your proper equipment at surface. Plus, most of geothermal reservoirs are, as known, let's say, green energy. Green energy classification is if you are below 350 kilogram per megawatt, it means you are in green energy plus. And unfortunately, in Turkey, active power plant, it is much higher than this. In order to be in class of green energy power plant, you should re-inject back. And now we see we have to re-inject, and now it becomes a question of how you're going to re-inject. When you produce from in natural reservoir conditions, CO2 is in supercritical state, but after you bring to surface, since your pressure is usually at the wellhead, it's much less than 76 bar, and when specifically you go after your condensate, it is much less pressure and temperature. Then it's become a gas. It's not a supercritical. Its management, its volume, it's become much more changed. And there is a two aspects: how physically you're gonna re-inject, plus how you're gonna, in a way, re-inject to do not change original mass balance, chemistry balance of your reservoir. The best way, when you design, before you make your first exploratory well, you measure your carbon dioxide or NCG rate and composition. When you design your power plant, your condensator outlet, to make a, let's say, re-injection planning with 100% of your NCG re-injected. Usually, it is going to be in supercritical state, even in with re-injection waters. Most of the re-injection waters are higher than 65 degrees. In anyhow, under pressure and above 65 degrees Celsius, your NCG is going to be in supercritical state, since carbon dioxide is a dominant gas to give characteristic to NCG, which is in this temperature and pressure condition, it is supercritical. It's preferable to make a less than 5%, since if you make a higher percentage, its mobility is much higher than brine. It can be dominant flow material. It should not be the, let's say, continuous medium in your brine re-injection, supposed to be brine too. Do not make an early mobilization of your communication between your production and injection well. And it's preferable if you have already power plant, you have an injection and production and injection wells, it is best to make a tracer test to define the path of your, let's say, brine, which way it's following mostly, which well is best to inject, which well is best to produce from the tracer test, and then you can maximize and distribute your NCG according to your tracer test result, which is the case actually in Turkey when we did, which helped better. And to come our pilot study, the SAK1 is very close to the city of Aydın, about 10 kilometers east of the Aydın city, and 7 to 10 kilometers, actually 87 kilometers to city boundary, but about 10 kilometers to city center. And the formation is a metamorphic. I mean, basically it is carbonate. Most of the Turkey geothermal systems are active power plant geothermal systems are carbonate. The reservoir section is carbonate. And Umurlu field is actually a discovery well for the Umurlu field SAK1. It is 2,054 meter, the reservoir section entrance. Of course, it's a very long reservoir section, but actual first main flow is 2,054 meter, and the temperature at reservoir is 154.5 degrees Celsius. You can see the stratigraphy of the well and the well design and the casing design, and maybe it's not very clear the production, injection, temperature, pressure profile also. You know, I mean, I want to actually mention a little bit here what we add to this. Everybody in Turkey want to re-inject CO2 NCC back, but after you send your steam, usually your NCG is separated from your brine at the wellhead. In separator, it's moved with steam, go to power plant. When you condensate, when you go through the condensator in power plant, you segregate your, you condensate down your brine and you release atmosphere your NCG. Your gas is your NCG is a gas. It's not a supercritical state or any fluid. Okay, then, in order to be able to re-inject it, you are going to inject a gas into a hot water, a fluid, which makes it a little bit challenging and difficult. At the normal surface wellhead condition, in order to be able to do this, you need an extremely high pressure or high temperature, different meteorology of the wellhead. You have to have a specific wellhead, but in a conventional production or re-injection well, to be able to do that, we come with a parasite string to be able to run in hole to a certain depth, which will ensure us the well is, as I can show here, in well we have a secondary string in a certain depth, in our case it's 700 plus meter, to make sure when the gas and brine is mixed, NCG is not a gas state, it's a supercritical state. For that, we make a design in order to be able to pumping a gas into a fluid is difficult, but by an ejector system with a motivated fluid, we use a system with a special design ejector, which is our actual main contribution to the project, is to vacuum gas inside the already going down fluid. Actually, I want to just mention here, the gas can from power plant here, NCG income, cool down, and then go to the compressor, compress it, and at the same time cool down couple stage, and we measure and make a final cool down. The cooler, the better. Actually, in this diagram, there is no chiller, but later on we understand the effect of cooling down at the surface to make it compressible more and more efficient. We put a heat exchanger as well, a more complicated heat exchanger as well. And then it comes to wellhead, and parallel way, there's a normal, just conventional small water well, fresh water, which is supposed to be a little bit cool. The effect of the coolness is important when you motivated this small volume, relatively, let's say maximum 10 cubic meter per hour water. This motivated fluid actually the one who vacuum the gas inside the energy to inside it with the Bernoulli equation main logic. It's ejector. It is the faster you pump this motivated fluid, I mean the water, the more gas you can vacuum and absorb with low pressure. Of course, you can pressure, but it's going to be high pressure, high temperature, the efficiency is going to come down. We will have a purpose of decreasing cost of third tone reinjection down, and that was why we designed this special ejector to make it cost efficient. At the same time, as you see, there is a brine reinjection system. The brine go down, the gas go down at the wellhead, and it is continues to go down. Since this motivated fluid vacuum and it's moving down, it's in smaller string. The speed of move down is not changing, but since there is a more the volumetric, let's say volumetric, it's mostly NCG, but mass related, it is 80% water. After a certain time, the column of the hydrostatic column of the water makes it's more pressure, and when it's come out of this parasite stream here, there is a NCG in supercritical state. There is a normal water and there is the outside brine. All these three just join, and even there is a two water and one gas, let's say NCG. All three act as if one fluid, since NCG is not a gas state, it is supercritical. Physically, it's acting like water. To go next, what we did, this is a little further details of our system. Actually, I explain all of it. This a little further detailed design, and the actual engineering is in here at how to vacuum a gas in a water. Okay, and to go next slide. This is the physical, like our fresh water pump, is our compressor, our cooler. There is some other heat exchanger here, as you see, for the intermediate section of the compressor. I want to little bit mention this compressor since we re-inject all these NCG as it is coming from well. There is a certain little amount of H2S, there is some CO2, there is some other minor gases. Without filtrating or without any purification, even there is some certain little amount of vapor, we compress all of them all together. We don't need to do any, let's say, filtration or purification for gas. We just collect it, cool down, pump as it is. For that, the compressor internal, let's say, surface should all be stainless, should be resistant to the high corrosive gas or high corrosive let's say fluid. When you compress this NCG, there's a certain amount of vapor under pressure. Some of it become liquid, and that liquid, like some CO2, some H2S, and then it could be very dangerous, highly corrosive. For that, most of this compressor internal, like piston, liner, everything is a kind of special ceramic coated. And this is our design, engineering design. This is the line where motivated fluid come. This is the line where NCG come. This is actually, there is a special ejector motivated fluid system in here, and this is the where it should be specifically designed to not make any restriction when after passing through the ejector section, it should be continuously without any restriction go down, and after that it can down and you can close it through anytime you want just to bypass. And I just want to come with the number, what we did, what we read on the surface, and then what was the results. The pump was just pumping around 9.5 cubic meter per hour, which is approximately 9.5 tons. It's the normal fresh water well water. The pressure was 56 bar. The water temperature was 16 degrees. This is usually around winter, and it is underground, near surface underground temperature grade. And the volume of the carbon dioxide was, let's say NCG or carbon dioxide was 280 cubic meter per hour. Under this temperature pressure, it is equivalent to 2.65 ton per hour. And pressure of the CO2 collected directly from the condensator of the power plant after, let's say, a couple of 100 meters of at the surface line to come to first cooler was 2.8 bar. Of course, inlet pressure is important for the compressor efficiency. The outlet was 52 bar. May it take your attention, the pressure of motivated fluid is 4 bar higher than pressure of the compressed outlet. And the brine injection was 72 bar, 72 cubic meter per hour, and the brine temperature was 64 Celsius degree. This is a typical binary, let's say, medium enthalpy power plant re-injection temperature, actually. I just want to say the first 20 days, it is still time by time using. In total, maybe it is over a couple of 100 tons of NCG re-injected, but this presentation was presented in 2018 in Nevada, Texas. These are the data we do there in our article. We totally re-inject 134,400 cubic meter, which is 1,248 tons NCG, and with 2.65 tons per hour, with 165 kilowatts hour energy consumption. Actually, it is one of the, let's say, in this class, one of the best low cost, high efficiency. This is coming from, let's say, using ejector and using motivated fluid and selecting, using a proper cooling system and the surface making optimization to, and plus using the well itself dynamic. The well, when you have an injection well, you have a continuously, let's say, 72 tons of brine in a certain speed and volume go down. We actually use this dynamic to help to make it much more efficiency, and this can be improved easily to 8 to 10 tons per hour. It depends on you have to change the compressor, you have to optimize the pipe, you have to optimize the ejector. This is a flexible thing. It's not a constant. It is totally depend on your compressor capacity plus your design of ejector and your well demand. How deep is your reservoir? How is your injection temperature? How much NCG you have? And our plan was, we are still working on some different projects to be able to re-inject about 1 million tons of CO2 per power plant for their first 20 years, which is expected minimum life cycle of each power plant. And I want to show something. This is usually, as I say at the beginning, the biggest scare. I know some other companies in Turkey was trying to directly inject CO2 into the brine with a compressor to the line without any secondary string. And immediately wellhead pressure increasing after a certain point. It is called bubbling at wellhead. They will not be able to inject CO2 neither brine. But in our case, if you see the first graph, when we start, it was around 2 bar, and then it's come to down. This well actually could get much more brine, and it could get much more NCG, but still 72 cubic meter per hour was re-injected in 2 bar. After a certain time, as you see, it's coming down since the downhole fluid mechanics and thermodynamics balance is coming in place, plus CO2 is with the brine make a certain acidic condition, plus the formation is mainly carbon dioxide. When you have a certain carbonic acid, that's a weak, very weak carbonic acid, for a certain time, slowly it's make a actually improvement in permeability, near wellbore permeability improvement. As you see, it was, you can see effect here very sharp, and then stabilized. If you go further, maybe it's gonna be pretty much stabilized around 0.5 bar, since the near wellbore improvement is already completed, and then it is maybe very, very slowly gonna be stabilized. The second one is the, when you measure your CO2 rate, or let's say concentration at your condensator, this is the first initial value of Aseke well. As you see, this well was, or this is, I think, one of the production well. It's not written here. It is the Aseke injection, the NCG injection. This is the power plant which Aseke production wells are connected. Is their average NCG? As you see, it's 1.2 per weight rate. I mean concentration. Let's say you produce 700. Tons per hour brine, and you produce about 8-9 tons of NCG at the beginning, and then it's come down slightly. And here, this is the first point we inject. Since Aseka was, after tracer test, was the best well to inject, and it was immediately, you can see, after actually 10 days, you can see the result. It was not increased, it was balanced. You don't actually create a new CO2, you just decrease, or let's say you balance the income and outcome to be balanced after a certain time. Of course, this is a very short time. If you make it 2 years, you're gonna see the balance much more, let's say, scientifically. I want to come to conclusion what we come out. First of all, re-injecting a gas into a fluid is not an easy task with an acceptable cost per unit. We successfully able to do that in Umurlu 1. Today, if I look, I mean, re-injection for 5 years increased average production more than, in our case, was more than 21 ton per hour in 3 wells production, which is related or connected to this power plant. It was increased 7% increasement in the brine, which is actually pay off its cost of NCG re-injection. It's keep continuity to not decrease. Actually, it is maybe in the first duration it looks like it's increased, but after a while it's going to keep constant, since you are not producing any carbon dioxide. Actually, like brine, you circulate in the same one. You're keeping your chemical, or let's say fluid composition in the original state. As you know, all in geothermal system, at the beginning it's very powerful. Step by step it's come down. You have to put pump or some artificial production. But if you're able to manage to, from the far beginning or at the level of speed your well is coming artesianic, you can keep your well forever with a natural flow if you're able to manage to re-inject NCG. And reservoir temperature was not affected. As I say, as soon as you keep, when you think the volume of the NCG we are injected and the total mass volume of the reservoir system, plus when you compare the total brine re-injected, as I say, it is less than 1.5 percentage, it is not a state to affect a big picture of reservoir, let's say, temperature model. As soon as you do properly, let's say, the reservoir temperature was not affected. Actually, this is keeping CO2 level constant. It is keep the production for a short term higher, and then it's keep constant, which is good expected, and it was as expected in calculation. I mean, as I say, the production increased. It was a short-term increase since effect of the first effect of the rebalancing NCG. But for a long term, it's not going to increase anything. It's going to keep its constant as it is original reservoir condition. As a conclusion, we come. Actually, we patented this. This is last slide of my presentation. We patented all this study in Europe, in US, in Canada, and this is one of the actually effective, low-cost, long-term, efficient NCG reinjection system. I can say basically, and I believe that it is it could be, if effectively be used, it could be much better solution than pump. This is actually end of my presentation. I'm here to just reply any question.
Wow, Ismet, thank you so much for your presentation and the level of detail that you presented. I think that's super, super interesting. And of course, you know, the questions are dropping in. So I'm just trying to group them in one way or another, but maybe starting with a few of questions of myself. You have had one pilot case so far, and you've proven it for 5 years. Is that correct? What you've reported?
Yes, it is correct. It's proven. It's working still, and yes, that's true.
And of course, I mean, the driver, I guess, in the Turkish context has been the CO2 re-injection. But on the commercial application, kind of what drives the interest for this kind of tools with the developers? Is this a commercial way of mitigating these gases, or what do you see as the main driver for this application in Turkey and beyond?
Actually, before designing power plant, if this is being considered, it can be motivated to keep your cost design at the beginning, or let's say the methodology of your production at the beginning, and keep that continuously. As I explained it, we set this system after power plant start working, after 6-7 months. And it is a secondary, let's say, adjustment to the power plant. Even it's working, since it is adjustment, it is not the perfect, let's say, alignment. In Turkey, there is over 45 working power plant for geothermal. We tried to modify to some of them, and actually we could not. I mean, we talked with most of the major companies like Zorlu, like Gurish, like other companies. They were all interested, excited, but at the end, we could not go further. I think there's two reasons for that, to be honest. One of them, we are as a MEA, they say we are one of IPM drilling contractor. We are just focusing mostly on drilling. This was just that time as our client's request. Did we as a being their solution partner. This is not our core business. We do that. Okay. We patented. We never focused 100% aligned since we are busy on some other projects. But it can be the best tool to keep sustainability of your reservoir from the far beginning. I can tell this clearly.
Yeah. And how applicable is, let's say, this technology for different situations in geothermal? I mean, you know, high temperature with low temperature, different gas contents, etc. Kind of how broadly applicable is that technology?
This could be applied all kind of geothermal system. The higher temperature, of course, is gonna be a challenger, since you have to manage that this carbon dioxide is very sensitive to to temperature specifically. It's a special molecule. But since we are using a secondary string, go to certain depth, when these NCG plus brine, some of the flash power plant, for example, your surface reinjection temperature is around 110 Celsius degree, it will be really normally almost impossible to pump a NCG gas into 110 degree brine. But with secondary parasite string, since you're isolating your NCG from the brine physically until a certain depth, it is applicable for all of them, but the surface energy requirement per unit re-injection, maybe 5% or maybe 7% going to be higher for higher enthalpy, which when I say higher enthalpy is 110 degrees Celsius re-injection water compared with 65 degrees Celsius re-injection water. But it can be applied to all kind of system. Of course, if in order to not damage or do not make any damage to the reservoir condition, to not make any additional, let's say, scaling or any other chemistry change, your reservoir originally should be producing some NCG. You know, I mean, I cannot say anything, okay, let's re-inject NCG in a reservoir with zero CO2 production, with normal brine production. I cannot make any comment. Most probably it's not going to be good or perfect application. But for any kind of temperature, let's say, or enthalpy-wise, or volume-wise, or scale-wise, for any kind of geothermal system, have a natural NCG production. It's not supposed to be specifically CO2, any kind of NCG. This can be applied to re-inject that exactly 100%, I can say.
Okay. And now the questions are trickling in, so let me see here how I can group this in the best way possible. One of the questions here, is there a danger of scaling at the re-injection valve because of the CO2 injection? And that goes in hand with the question about that supercritical CO2 combined with water being very corrosive. Do you have any experience and comments on that?
Actually, as I say, you know, brine at 65 degrees surface go down step by step, increased temperature. Let's say in touching reservoirs 85 degrees Celsius, you have a almost same temperature NCG, and the NCG is partially soluble in that brine. The rest is as a supercritical state, carbon dioxide, like a secondary fluid moving with brine. All we know, you know, the amount of CO2 solubility with water is restricted with the temperature. In reservoir condition, or let's say in a re-injection well condition, the amount of CO2 soluble in the water, let's say, or in brine, is very limited. Then it's a very low possibility to damage casing or any your well equipment. For example, our client in Azteca 1 well re-inject, even sometimes use system a reverse for a production pump in same well and depend on the day demand. Nothing happened. They don't change anything in wellhead. They don't see any claim about the casing or anything. And in one stage, we have to pull out this parasite thing was coiled tubing pipe. We have to pull out and be replaced with a new pipe. The purpose was to put a stainless, like a galvanized pipe. The pipe come off the surface was quite in good condition, quite in effective working situation. The things could be, let's say, for long-term application, I can say, if you use the coil tubing pipe or a parasite string, if you pump a high volume of, let's say, it's almost pure carbon dioxide, for long-term, you should be careful. It could be like brittle. When you pull out all, you should be careful to not break it. It can be brittle to break down, and you can lost to drop in well. That is the point. You should be careful, since CO2 could make a certain material brittle. But our secondary string is an ally. I mean, the coil tubing is an ally. It is good for CO2 to injection, but still you should be careful, which is close to surface.
Okay. Here comes the next one. Do you need a specific wellhead to reinject the CO2, and would it require a specific metallurgy to withstand the corrosion?
No, no. It is wellhead, since wellhead is not seeing any CO2, any NCG. Your NCG is touching well after 720 meter in our case. So in that condition, the CO2 is, as I think there is a one key sentence in my presentation, apologizing my language, CO2 after 33 degree and 76 bar, it becomes supercritical. Supercritical means physically it's a fluid, but chemically it's a gas. So which make it, I mean, it is 720 meter, it's not affecting well at all. Plus, since it's a supercritical state, even after that depth, let's say from our case, from 720 meter to 2054 meter, since the carbon dioxide or NCG itself is a supercritical state, its effect on corrosion is minimized due to the, let's say, fluid mechanics or chemistry or enthalpy or thermodynamic condition of in the well, in the distance where brine and NCG go down.
So to understand this correctly, because that's a separate question here, the mixing of the water from the pump and the NCGs from the compressor happens at a depth of 720 meters.
Yes, that's true. Yes, yes.
Okay.
I mean, there is a fresh water at the surface with NCG in coil tubing. It's a special pipe with LI. The normal well, let's say, brine of the wellhead, exposed to the wellhead, and normal brine you make from your power plant to re-inject from your system to the reservoir, join back in 720 meters. You isolate your fresh water NCG composition with a special LI pipe. Then from your wellhead, don't touch any part of your wellhead bath or anything, and it is isolated actually. It's not effective. You don't have to have a special wellhead or specific metallurgy in your wellhead. A conventional wellhead is okay since your NCG is never touched your wellhead.
Here comes another question. I think that's a bit more general, but the way you describe it, basically, it's you utilizing the CO2 that is being produced by the production well. But here's the question: if your technology could be a way to inject CO2 coming from another source into the same well, or would this only be applicable for a non-producing, let's say, reservoir setup with two wells?
Yes, it could be, as I say. For example, it depends on your reservoir. Let's give an example. For example, in Zorlu field, it was when you first start production, it's one of the famous Kızılderili field. It was almost 4% CO2, NCG, let's say. Now it is below 1%. And they lose a lot of NCG. Today you can pump or collect CO2 externally out of their system, pump additionally, since they already lose a huge amount from their, let's say, reservoir mass balance. Or regardless of that, it depends if your reservoir characteristic or chemistry can absorb CO2, for example, specifically if it's a carbonate, or it could be some other formation. I'm not specified on this formation chemistry, but as I know, as soon as carbon dioxide entering in reservoir, it do not make any block or any restriction in long-term reinjectivity. You can pump as much as you can. You can even pump supercritical pure carbon dioxide, but how efficiency, what's going to be cost per ton your reinjection? Yes, you can do, but it's a question of what is going to be cost, what's going to be the efficiency. But to come to your specific question, yes, you can bring externally, bring carbon dioxide from another source, re-inject into a geothermal system. Actually, for a certain time, it's going to help greatly to make your geothermal system much powerful, much more efficient. Yes, you can do.
Okay. Here come some questions. Let's start with this. I mean, you mentioned that one of the points that you have is that the that re-injection basically has increased production, and that would be meaning the production of the fluids for the plant, correct?
Sorry, can you ask again? I didn't get it. I apologize.
Understood. So yeah, so I'm trying to rephrase. So in your conclusions, you basically said that from the experience, I'll just trying to read this here, that the produced CO2 increased in production wells after CO2. That was not the question. The question is that the CO2 reinjection increased the average production more than 21 tons in 3 wells, corresponding to an increase. And that refers to the production of the fluid, correct?
Yes, that's correct. It's not a CO2, of course. The whole power plant, regardless of this brine injection in the whole system, the total CO2 volume was less than 9 tons. That 21 tons per hour is brine increasement, it's not the CO2 increasement. CO2 increase is very negligible, to compare. But for a certain time, it is go up and then it stabilizes. Since you don't creating any additional CO2, you just keeping the balance.
Okay, then a concrete question to that here, and that's a question likely from the US. You say that CO2 in the production wells has increased after the re-injection. Will this continue to increase until the CO2 level is so high that injection is no longer practical? Because this is what occurred in a CO2 injection experiment at the COSO field in California.
Can I ask the question again? Sorry, I apologize.
Yes. Oh, no, all good. So the question here is that you said that CO2 in the production well has increased after starting injection.
Yes.
So the question is, will this continue to increase until the CO2 level is so high that injection is no longer practical?
No. It is, look, I mean, you produce, let's say in our case, 8.3 tons, it goes to 8.5 tons. It is gonna, let's say, stabilize forever for 8.4 tons. I mean, your brine CO2 concentration is a totally matter of your in reservoir condition when your fluid enters to your wellbore, thermodynamic condition, pressure, temperature, and pressure temperature is affecting how much carbon dioxide molecule is going to get freed from the carbonate, calcium carbonate and calcium bicarbonate. The only difference is there's one more carbon dioxide molecule. Okay, you are not creating any different condition in reservoir to produce a new carbon dioxide, or you don't adding additional carbon dioxide to the well. You producing 10 molecule of carbon dioxide from your system, you re-inject 10, your balance is there. Nothing changed. As I say, when I say it was a far beginning, the first week or 10 days when the first brine arrived to the surface, the brine with the CO2 we re-injected arrived to the surface, it's motivated since it is go down, it's balanced, slightly go up and stay there. It's not going to affect at all since you are not creating any additional CO2 in your reservoir condition, thermodynamic or enthalpy or let's say chemistry condition. The main condition of your reservoir is not changed. The pressure, overburden pressure, the temperature, nothing is changed.
Okay. And then here a question, I'm just trying to simplify this a little bit, but there have been discussions about CO2 as a working fluid for geothermal energy extraction. There have been discussions about using CO2 as working fluid for geothermal. So the question is here, do you think that CO2 can increase the efficiency of geothermal plants with re-injection purpose like you do?
Our case is brine, I mean water is the main, I say, continuous medium in the whole section of reservoir management. If you use CO2 as a medium, as a main your reservoir fluid or material to collect more enthalpy, as I know, CO2 molecule is much more attractive, much more effective than the water molecule If your system is totally established on CO2, it could be much more higher enthalpy efficiency. But our case is different than that. Our case, we have a geologically settled system. We are just, we have a 1.5 originally CO2 percentage. We try to keep that 1.5 to make its natural production and keep the reservoirs mass balance and enthalpy condition to make it forever sustainable. But if you have a system, you directly pump CO2, it's a main fluid instead of brine using CO2 as a main fluid to circulate, let's say hourly 500 tons of CO2. This is a question. Maybe I cannot give a exact answer, but as I know, CO2 have a higher efficiency for the enthalpy carrying. It could be better than brine, or let's say better than water, since first it's much more effectively affected for enthalpy transportation. Secondly, it's let's say supercritical state changes in wellbore can help to generate a series power. As I say, if you have a more than 1.5 or 1% of CO2, it affects your natural productivity. If you have a fully, let's say, pure CO2, it could be much more strong, but is it going to be at wellhead manageable to manage that much CO2 expense? You know, when you expand from supercritical to the gas state, you actually CO2 itself lose some enthalpy, which is collected from the whole well enthalpy. But since it is making the volumetric change to the enthalpy, that CO2, let's say, still from the brine is much more effective. It's make your well natural without pump production. For, let's say, this combination, less CO2, high water, it's help as a natural pump. But if you come to, let's say, fully CO2, it's a question of expense. You have to test it. But I know that there is some certain closed loop system. In order to decrease the closed loop system surface pressure or energy consumption decrease, a secondary stream could be lowered down in production well to re-inject CO2 to make a natural like a gas lift. Since it's supercritical state, it is the temperature, pressure, sensitivity, and efficiency. It could be, but for whole system as a carbon dioxide system, as a closed loop carbon dioxide geothermal system, it's a little bit further than my knowledge. Let's say.
Okay.
Need
okay.
to be experienced.
Okay. Then here one question. We have to get to the end here, but whoa. So here one of the question is that at Ümülü, have you experienced any reduction or improvement of injectivity over time?
Yes,
the question
I said
is,
yes.
The
Exactly.
CO2. Go ahead.
Yes, exactly. In Umurlu, as you see from the wellhead, when I was re-injecting CO2 in that well, initially we don't change the volume, the brine volume, the carbon dioxide volume, nothing. It was start with the 2 bar, it decreased to 0.5 bar, it stayed there stable. But it do not mean it's going to affect all of the reservoir. If brine with carbon dioxide, which means a weak acidic with carbonic acidic formation, I mean, when your injectivity point, your point when your brine first touch your reservoir system, if it is sensitive for solubility to carbonic acid, yes, it's affecting. In our case, it was, and it affect is increased injectivity.
Okay. And then here, what if the NCGs are not pure CO2 in the mix? What if there's methane in the mix?
I don't know. In our case, there was a very, very minor methane, let's say 0.001%. We don't filtrate, we pump it all, since we say it's NCG reinjection, actually it's not a CO2. Again, I say I didn't experience this. It's a matter of attitude of methane to, let's say, to pressure temperature. I mean, methane's volatility, molecular characteristic need to be investigated. How it will act in overburden pressure, in reservoir condition, pressure, temperature, in stream, in flow, that need to be investigated, to be honest.
Here, a question to, is there any impact in the surroundings of the wells, like an increase on the CO2 released after the injection?
Yeah, no, as I say from my presentation, in the first couple of weeks, it goes slightly up, but it's stabilized. Since your system, it's already have a huge balance. Actually, you pumping, let's say, 2.6 tons of carbon dioxide to a huge system. All of it's not directly like a pipeline connected to other well. Maybe some of that is going reservoir slowly, percolated to other non-active places, or just don't directly go to your production well. But since it's active, well connected, let's say, highly porous, highly permeable carbonate formation reservoir, yes, we see effect. But it was, let's say, from whole system, let's say there was a two power plant next to each other. The one power plant production well connected to this reinjection well system, as I say, after tracer test, we decided this well. It's go first from 8.3 to 8.5 and then come back to 8.4 and stay there. It is still around there, it is not making a extreme or significant change in up or down. It is due to the percolating time, or let's say three-dimensional percolating in the reservoir. For a short time, it look like it's going to go up, but it will not. It's go up and come back stabilized. If you feeding a 100% make a closed system, it's going to stay stable, not up, not down. Since the wells carbon dioxide accumulating or production as a percentage, it is totally a matter of your overburden pressure in reservoir condition and your temperature, your formation, let's say pure material. Is carbonate, is it basalt, is it dirty carbonate, is it pure carbonate, is it calcium carbonate, calcium bicarbonate? It's totally depend on that. It's not to depend on what you're pumping or how much you're pumping. Of course, if you pump pure carbon dioxide in a huge volume, you're gonna make it your main fluid in reservoir as a carbon dioxide, which is not the case in our situation, let's say.
Excellent. Okay, and then here are the last two questions, which I will combine in one. And we don't have much time left, so let's just quickly check this through here. Question one, will cooler or hotter brine be more efficient for the CO2 injection? And secondly, kind of does the composition on the percentage of the CO2 in the production fluids make a difference on the efficiency of the plant? So first,
I didn't understand neither of question. Can you ask again, please? Apologizing for that.
So then one and one. So the first question is, will cooler or hotter brine be more efficient for CO2 injection?
Yes, cooler brine is better. Maybe it's not going to be significant. The cooler brine, the better, or it's going to affect your reinjectivity slightly better, since just below wellhead, your brine and your reinjection string, a secondary string, is touching each other. There is immediately start let's say heat exchange. It's depend on the pressure, the let's say speed of your NCG and motivated fluid in the secondary string. How fast it's go down? Is it making a back pressure? If it cools too fast, it's going to make a back pressure. It is enough speed up to not be affected by even enthalpy seriously. It will not. It depends on how much temperature, how much you're pumping. The higher CO2 you pump, let's say, it's going to be less effect. But the cooler condition is better to manage CO2 easily.
Okay, and I think at this point I need to stop here. We run out of time. Thank you so much, Ismet, for joining us today and for your thoughtful presentation. Thank you so much.
Thank you, everybody.
For our participants, thank you for joining us, and join us in 2 weeks for the next webinar. And for now, have a great weekend. Thank you all. Goodbye.
Thank you all. Thank you. Bye-bye.